one chapter. Yes, we're just going to be spending time in chapter 11 for the rest of the time here. So we did chapter 6, chapter 7. Now we are here. So this is how we're going to wrap up the class. We're talking about sequences today, and then Tuesday, Wednesday, and Thursday are going to be talking about series in some fashion. So that'll be good, and then the last few days will be okay. Anyway, chapter starts off with this notion of something called sequences. Okay, and a sequence is simply just going to be a list of numbers, essentially, in some way. They might usually they're related in some way, right? There's some sort of connection between them, right? Maybe so. I have some examples written here, like 1, 2, 3, 4, right? It's just a sequence of my natural numbers, right? I start at 1 and go to the next one, then 3, then 4, etc. Right? Or I might have a sequence that goes 3, 1, 4, 1, 5, 9, etc. Right? Anybody know what those numbers are related to? Yeah, it's pi. There's the digits of pi, right? Just starting at the beginning and then working our way, right? So that would be the sequence, right? And then also we have kind of a fancier sort of sequence called the Fibonacci sequence, where the first two terms are called 1, right? So number 1, 1, 1, which I have here, and like this notation as well. And then each term after is just taking the first two terms or the two terms of 4 and adding together, right? So 1 plus 1 gives me 2, 1 plus 2 gives me 3, 2 plus 3 gives me 5, 3 plus 5 gives me 8, 5 plus 8 gives me 13, etc. The list will go. Okay. Yeah, these are some just basic examples. This one pops up quite a bit and is very interesting to study in a lot of ways, but this is what sequences are, okay? So to start us off, we don't even get to any of this yet. We just kind of want to be able to dissect these a little bit, saying if I first making a sequence and then going from the sequence to see what the general term looks like. So I'll just fit in the space here because really they don't take very long to do, but need to talk about them anyway. So we're going to do number 4 first, where we're just asked to list first 5 terms of sequence. Okay. And the sequence that we're given, right? So again, the general how a sequence is generally written is that you have like these little braces on the side with the A in the middle, and then you'll have A1, A2, A3, A4, right? But in general, you're going to write, in order to denote a sequence, you're going to have some A in term, and that A in term is going to be defined by some sort of setup, which in this case, A in is defined as n squared minus 1 over n squared plus 1, right? So every term fits into this mold somehow, right? We just have to take whatever numbers, like the first, it wants us to find the first 5 terms, so I just need to take 1, 2, 3, 4, 5 and plug it into this guy, right? Because I want to get, for example, I want to get A1, right? I don't see what A1 is supposed to be. Well, that means n is 1, so I just need to take 1 and plug it in, so I get 1 squared minus 1 over 1 squared plus 1. What's 1 squared minus 1? 0. And 1 squared plus 1 is 2, but that doesn't really matter. So the first term of our sequence there is going to be 0. Okay? So now let's just work from there, right? So we have 0. So what number do I need to plug in here next? 2. Okay. So what do I get on top? Let me plug in 2. So you end up getting 3 over 5, right? So it's just 4 minus 1 over 4 plus 1. So we get 3 over 5. Okay. Now when I put 3 in there, I'm going to get 3 squared, so 9 minus 8, or sorry, 9 minus 1, which is 8, over 9 plus 1, which is 10, which we could write as 8 tenths. So maybe So A3 is the same thing as 8 over 10, but that's the same thing as 4 over 5 as well. So figure that would be. Okay, let's just do another one, right? If I do, so 4, I'm going to get 16 minus 1, which is 15, and 16 plus 1, which is 17. So we're going to get 15 over 17. And finally, if I do 5, I get 25 minus 1, which is 24. And 25 plus 1 is 26, which we can simplify that a little bit. It's going to be 12 over 13. So okay, so you're literally just plugging in for each term, right? And so that would be the first 5 terms, and it continue from there. Does that make sense? Is that good so far? Okay. Hopefully not too bad. I'm going to leave you a bit of time to write that just to expand it a moment. I'll probably erase this here. Okay. Now we'll do, so let's see, I chose number 8 next. Okay, yeah, that's good. Okay, so we're going to do number 8 now, which is the same sort of question, but now we have 8 sub n is equal to -1 to the n power times n over n factorial plus 1. Okay. Who remembers what n factorial is? Who can tell me what n factorial means? What do I do with that?
It counts down.
You multiply
Good. Yeah. So you're counting down each time, and but you're multiplying each time as you go, right? So for example, 4 factorial would be 4 times 3 times 2 times 1. That would be 4 factorial. Okay. So let's go ahead and get all the terms of our sequence here, right? Okay. So if I put 1 in there, right? Let's just go to each piece, right? I get -1 to the 1. It's -1 to the 1. -1. And then we get -1 times 1. So there's a -1 on top over 1 factorial. Okay. What is 1 factorial? 1 factorial is just 1. Right? So we get 1 plus 1, which is just 2. So -1 over 2 is the first term. Okay. Moving on from there, I go to 2, right? So -1 to the second power, what's that? 1, good. And then 1 times 2 is 2. So we get a 2 on top over, and then we have 2 factorial, which is what? 2. 2 plus 1, which is 3. Okay. Okay, 3. What's -1 to the third power?
-1.
-1. What we're going to notice is that if I take it to the fourth, it's +1. Fifth is -1. Each time you're going to have a negative kind of alternating on each of these terms. So we get -1/2, 2/3, and then we get -1 times 3, so -3 over, which you can put in front or just leave it on top, doesn't matter. 3 factorial, 6, good. So then we get 6 plus 1, which is just 7. Okay, 4 factorial, we already wrote out. What is 4 factorial going to end up being? Yeah, so we get 25 on the bottom. -1 to the fourth is 1, like I said, and then 1 times 4. We get 1. So notice each time, and maybe I'll write this again. See it here. We get 1, 2, 3, 4 on the top in each case, right? And then it's just flipping signs, and on the bottom it's just whatever n factorial is plus 1. Okay. Finally, we will do 5, right? So -1 to the fifth power is what? Yep. So we get -5 over, now 5 factorial is 5 times 4 times 3 times 2 times 1, which is what? 120. So we just get 120 plus 1, 121. Okay. So again, just plug it in. Okay. Just plug in, you get all your terms, right? That's as simple as that. Okay. Just want to make sure everybody's kind of getting a hold of that, right? Because we're going through nothing too bad, right? Okay, so that's number 8. And then I wanted to do an example that wasn't just like plugging in the numbers first. So let's take 10, which is going to be where we start off and we're given that A1 is equal to 6. Okay, but then we're given that a of n plus 1 equals a n over n. Okay, so a1 is 6, and then a n plus 1 is a n over n, right? So we already have the first term of our sequence, which is 6. That's good. Okay, so according to this, what this says, to get the next term of the sequence, I need to take, right? So I want to get a2, right? So I'm going to take n equals 1 and plug it in here. So I'm going to get a2 equals a1 over 1, right? That makes sense? I just plugged n equals 1 into that, gave me a2, which is just a1 divided by 1. What is a1 divided by 1? Yeah, it's a1, which is 1, which is 6. A1 is 6, right? We established that at the beginning. Okay. Next, I'm going to put a 3 in here, or sorry, I want to make n equals 2 now, right? Because when n equals 2, I'm going to get 3, and we're going to get a2 over 2. So a3 is going to be a2 divided by 2. Does everybody see that? Okay. So a2 is 6, so it's a2 divided by 2. 3. Good. So then we continue from here, right? So the next one, I would take a3 and divide it by 1. a3 divided by 3. So what is a3 divided by 3? 1. And finally, to get the fifth one, n would be 4, right? So I'm going to take a4 divided by 4. a4 is 1, so what's a4 divided by 4? Just 1. So that would be my answer. Okay? Really just a little plug it in here, okay? Does that make sense to everybody? Any questions here? A little bit. Okay. Make sure you can kind of set up. If I give you the term, you can set up these pieces. Okay, we're still not to that yet. But I have a couple more examples to do here. So. Okay, now, let's say that I'm not given like each term of the sequence and asked to write the first 5 terms. But let's instead say I'm given the first 5 terms and I have to say what the connection is between all the points. Okay, so that's what we're going to see in problems like number 14. So number 14, we want to find the formula for a n. Okay, so we're going to find, instead of being given a n, find all the numbers, we're going to find the formula for a n. Okay, now in these cases, you're just going to assume that the sequence is always going to stay the same, that the pattern is not going to change after the first 5. You assume that it's going to stick it through, right? So you don't need to worry about, oh, it looks like these ones are this far apart, so then the next one's like 500 or something. You're like, well, now what do I do? Okay, so number 14, we have 4, -1, 1/4, -1/16, 1/64. Okay. So this is where we got to use a little more brain power to say, okay, what is the connection between all of these, right? So maybe what's the first thing that's going to jump out to us potentially? It's the first. Yeah.
The negative sign alternating.
Okay. Yeah, absolutely. So the negative, yeah, and so the negative signs alternating. Also, we have on the bottom, at least for these terms, we have powers of 4. We have 4 to the first, 16 is 4 to the second, 64 is 4 to the third. Right. So maybe let's acknowledge that for a sec, right? So we have 1 over, so this is 1 over the 4 to the first, right? And this is -1 over 4 to the second, and this is going to be 1 over 4 to the third power. And yes, we have alternating negative signs, so somewhere in there we're going to have a negative, just like in example 8, we might have a -1 to some power, right? Now, it may not be in, we'll just have to think about it and make sure it matches up, okay? But that will be there somewhere. Now, if we assume that this is the correct pattern to look at, right, and it matches these ones, maybe let's try to take it back and see if it works, right? So what's the number before 1? 0, okay. So we'd have negative, right, because it should be alternating, and it'd be 4 to the 0. Okay, what's 4 to the 0 power? 1, so we get -1/1. That's -1, right? So that works. Okay, so the ultimate test, I'm gonna write this -1 off to the side for a moment, is to see if this one works. What's the number before 0? -1. I have 1/4 to the -1st power. What's that 4 to the -1st power gonna do? It's gonna come up as a 4, right? So that works. So this is absolutely the pattern we're looking for. Okay. So let's try to write that down, right? So we're gonna have AN equals. And then we have so our signs alternate, right? Now here's the question, right? We need to figure out what that power of the -1 is going to be. Since it's alternating, there's going to be some sort of -1. We need to figure out exactly what that power is, right? Let's see, if it was just in, let's think about what would happen, right? This is supposed to be A1, right? Always the first term is A1. So when I plug 1 in, I would get -1 to the first power, which is 1. What's -1 to the first power? -1, right? Okay, but is this first term negative? No. So the easiest way to fix that is just to add 1 to it. Or you can subtract 1, it doesn't matter. You just need to move it over, right? Because now that first term, A1, right, is going to be 1 plus 1 is 2, so it'll be positive. And then the next one would be negative. So just shift it, just kind of like shift it over 1. Okay? Good. Now we want to have 4 to a power, right? Now is it just the n power? No, because that means we would have 4 to the first power of the first term. What is it? Well, if it's n plus 1, I'd get 4 squared as the first term.
N minus 2.
N minus 2, right? Because I want A1, right? When n equals 1, I need it to give me -1. So I need 1 minus 2 to be -1. When I want 0, I want 0 to A2, so 2 minus 2 is 0, right? I need 3 to be 1, so 3 minus 2 is 1, okay? And this gives me each term, and so this therefore satisfies, right? Now, again, if you want to make sure this is correct, just plug it in and make sure it works, right? But that is going to be the AN term, okay? Make sense? Okay, we're going to do another one just so we can see it. That's the idea we're going for, okay? So I'll leave it up for a second. Sit, and then I can get over to talk about this before I can reset. Okay. The next one I have is number 16. We probably won't do all of these, but I wrote this. I thought they were so 16, we have 5, 8, 11, 14, 17. Okay, final formula for AN, right? So, everybody see a pattern here? Good. Each time I add 3, right? Right. So we want A1 be 5, right? And then A2 is going to be 5 plus 3. Right? Because that's going to be my next term, right? And then A3 is 5 plus 3 plus 3. Right? And then A4 is going to be 5 plus 3 plus 3 plus 3. And A5 would be et cetera, right? So each time I'm adding a 3 onto it, right? Now you have the full freedom to say, okay, well, let me just write down the numbers, or if you want to say this is 8 plus 3, that's fine. I wrote it this way though, in particular, to really highlight something, right? I have my starting point, right, which is just 5, right? I need A1 to be 5. And then each time I add a certain amount of 3s, okay? How many 3s do I add in this case? 1, which is 1 less than the number here, right? In this case, I had 2 3s, which is 1 less than 3. I had 3 3s here, which is 1 less than 4, and then 4 3s, 1 less than 5, etc. Right? So, what that gets me thinking, right, is that for each AN, right, I'm taking 3 and adding it not n times, but n minus 1 times. And the way that I represent that is I take 3 and I multiply by n minus 1, right? Because that says I add 3 n minus 1 times. Okay. Now, that's good for this part, but I need to make sure I start with A1, right? So what else needs to be here? 10. 5 plus 3. 5 plus 3 times n minus 1. Okay. And it's really that simple. You could also, so this is, I think this is like what we really need to go for here, right? Because you just want to be able to say I plug in n and this is the value I get. You could also think about this as if I had A1 equals 5, then AN equals say AN plus 1. You could also think about it like this, right? So if I start at a starting point, and then each time afterwards, I just add 3 to the following term. But this is more, right? In this case, I don't have to worry about all this AN being on both sides work. I can just add the one term. So this is the answer we want. Okay, good. Does that make sense? Okay. If you're given like some of them might be a bit more difficult, maybe like in the book, depending. If I give you one on homework, it should be pretty straightforward. Okay. If you don't recognize some of the terms, right, like in the last one where we didn't know about the 4 and the 1, try to do the ones that look like they're similar first and see if you can build something. Okay. Good. Any questions here at all? Yes.
Do you want to state what A1 is and then make a note, like just to continue?
I mean, kind of like what I had written here. I had A1 equals 5 and then AN.
No, like, well, kind of, but like have better answer. Like for example 10, we have A1 equals 6, and then we have the formula.
Right. So I wouldn't, in this case, I wouldn't recommend that. Like, I wouldn't do that. These problems, you should be able to write them in this form. Those are usually reserved just like, just like examples of building a sequence, but they're not the most ideal way to write it. So I would write it this way. Even that Fibonacci sequence I wrote earlier, we have ways to write that without having it look complicated, which it looks kind of gross itself, but it's still like more preferable than having like terms defined as the terms before it. So this is preferable. Yes.
So does and have to be?
What is it?
So like you have an on this side, you have and plus some other variable.
The AN over here should be by itself.
By itself.
Yeah, and then you can have everything adding to n, subtracting from n, whatever over here, and n is the power, but that should be by itself. Yeah, absolutely. Okay, good. So Your first few problems on your homework are gonna be just like this. Just like 4 through 60 here we just did. Okay? You're gonna be just finding the first 5 terms, or you're gonna be finding what the formula is. Okay? Good. Now, the big thing about this chapter, right? Remember, we in section 7.8, we discussed improper integrals. And in that section, right, we had 2 terms. Those terms were convergent and divergent, right? And those are very, determined, oh, if this integral gives me something, then it's convergent. If it doesn't, then it's divergent, right? Those 2 words are going to consume basically all of our week. We're just going to be talking about things converge or diverge, okay? And so that's something really important we want to do. So when we're talking about sequences, right, it's going to be different for series a little bit. For sequences, so every sequence, right, if it has an infinite amount of numbers, you would hope it ends somewhere, like it's kind of going towards some point, right? Some of them, like the pi one, obviously, which I erased already, but are going to be a little bit fluctuating, a little weird. But if you have some sort of like formula, right, you would hope that there's kind of a building point, right? Like, oh, this is going to end somewhere, okay? And that thing at the end, like all the way towards infinity, is we're going to call it L. Right, our limit. Okay. And we write that the limit as n approaches infinity of an, of this kind of an term here, which we might know, we might not, depends. And then we will know for our problems, but is equal to L, or that's the same thing as saying an approaches that L number as n approaches infinity, right? Now, in some cases, L might not exist. In some cases, L might be infinity, right? It might just be, right, in this case, this one's just going to keep getting bigger, but we still want to have that notation in mind, okay? And I read that here. If L exists and it's not infinite, the sequence converges, okay? So if some number pops out, right, whether that's 0, 1, 2, 3, or square root of 2, just some finite number, right, then it's going to converge. Otherwise, if it doesn't exist or it's infinite, right, then the sequence is going to diverge, right? Which means that it just keeps getting bigger, or that it just doesn't work, right? And if you want an example of one that maybe doesn't work, let me kind of draw up something for you real fast. Okay, so let's say that I have a sequence that is just -1 to the n power, right? And that's it. Okay, A1 would be -1, A2 would be 1, A3 would be -1, A4 would be 1, A5 would be -1, A6 would be 1, A7 would be -1, etc. Right? This just keeps going up and down. It's not like going towards anything. It's just going to either be -1 or 1, so it keeps hopping up and down. Right? So this ultimately is not going to. It doesn't converge to one to the other. Right? It's always flipping. It's not like kind of slowing down. It's not building towards some point. It's oscillating constantly. And it's not going this way. It's just straight, right? So in this case, the limit wouldn't exist. So this would be a divergent sequence, right? But a convergent sequence would maybe, and I don't know a specific example I can write for now, but would look something like this, right? Where you notice that these points at each time like are slowly moving towards that center line, right? So now there's something it's building to, right? If I were to kind of connect these with a line of sorts, then you can kind of see, oh yeah, it's kind of slowing down eventually, right? So this would be an example of some like a convergent sequence. We're going to do some examples more concrete, like plug it in, but that's kind of the difference between divergent and convergent. And obviously, of course, if I just have a function that, instead of all these points, just goes to the sky, then that's not convergent with it. Okay. Also, we have a couple of things to mention here when it comes to this. This one might be pertinent, and this one, I don't see this one, you have to use this one, but I want to mention it anyway. This first one says if the limit is x approaches infinity of f of x is L, right? So we have some function and its limit is gonna be some number, right? Or it's approaching something. And if that function evaluated at my n, number n is gonna be an, like of my sequence that I have, then the limit is n approaching infinity of an is also L, right? So what this means, right, is, right, so let's just take examples, right? What is the limit as x approaches infinity of this sequence? I'm sorry, of this function, right? As I go towards infinity. Any guesses? Yeah, it's not a little bit. Zero. Not zero. What is it? -1. Not -1. So in these examples, remember what you would learn from Calc 1 is that, oh, I would want to divide a power of x from the top and bottom. But in this case, right, or if it's just polynomials, right, we just look at their degrees, right? Is the degree of the top and bottom the same? Okay, then the limit is just going to be the ratio of the coefficient of the highest degree terms. So we have x squared and x squared, 1/1. So the limit of this thing is, okay. I don't have time to review how to do those limits, so with everything. So try to recall that because you're going to do some of those things. Okay. Now, what happens if I put n in there instead? Does that look familiar to us at all? Anybody? N squared minus 1 over n squared plus 1. What is it?
Sequence.
Well, it is a sequence. Which sequence is it? It's the first one we did. That was the sequence we did at the beginning, right? So the limit of this is 1. We know how to evaluate that. So, and if I put n in, right, into my function, that is just the sequence, right? So that means that the limit of this sequence is equal, okay? That's what that says, okay? If I know that's 1, and if I plug in, it's my sequence, then it's the same limit, right? You don't necessarily have to do this sort of transition on every problem, but just know, oh, I don't need to treat this differently. I can do it like limits I've done in the past, okay? Use similar, right, still. So any sort of tricks you learned in chapter 1 of the book, L'Hopital's rule still works, right? All of these typical, like the things we learned before still are going to work. Okay, good. We also have this notion of the squeeze theorem, where if I have 2 sequences or 3 sequences, where there's 2 outer sequences and the sequence in the middle is in between them, right? For some, and I say here, that just means it's some number, some natural number, 1, 2, 3, 4, 5, 6, 7, whatever it is. So that's true for all numbers greater than that specific one. And if the limit of the 2 outer ones equals L, then the limit of the inner one must also equal L, right? So it kind of like says, oh, well, these ones both go towards L. And if this one's in between them, then that also has to go towards L. It's not like you can just break out. It has to follow where they go. Okay. And the final thing I'll mention before we do some more examples, if the limit is n approaches infinity of the absolute value of a sequence is 0, then the limit is n approaches infinity of that sequence is 0, right? So all that's going to mean is essentially, if I have a sequence that has like a -1 to the n on it, just when we were talking about the graph there, it was, oh, that might be a little weird to work with, kind of getting with numbers. But as long as that sequence without that -1 to the n on it converges, then with the -1 is also going to, like if it goes to 0, then that one's definitely going to go to 0 as well. Okay, so we'll probably do an example one more like that, but something to keep in mind. Okay, good. So that's all about limit stuff. Our goal is to be given some sequences and see if they convert or not. Okay. Any questions on that? No. Okay. On the right, on the full right side of the board, I just have written some laws, which are very similar to limit laws you learn in chapter 1. They just apply for sequences. Most of those are pretty obvious. Like, I'm not gonna have you write those down for me when you're doing your homework or something, but I wanted to write them down so you have them, just to know that I can split it up in this way and this way and this way, right? Notice with limits, I can just go take it to each term, right? And with division, I can take it to each term, right? I can't do that with derivatives and integrals, okay? So it's okay here, it's not okay there, right? Okay, so let's do examples. Okay. So we're gonna start with number 24. Okay. So let's write determine convergence. Just save some time here. So we're just going to say if it converges or diverges, right? Again, if it exists and is not infinite, it converges, otherwise it's divergent, okay? And if converges, find limit. Okay? So if it does converge, we want to state what the limit is, exactly what the limit is. That gives us the right answer, okay? So we're going to start with number 24, which is 3 plus 5n squared, so an equals 3 plus 5n squared over 1 plus n. Okay, so in all these problems, if I want to determine if it's convergent or not, then the limit, I'm going to take the limit of the thing. Okay, so any guesses on what the limit of this thing is going to be? So we have 3 plus 5n squared over 1 plus n. It's infinity. It's not going to be 2 in this case. It's going to be infinity. Okay, why is it infinity? Good. Yep, you're all right. So the power on top is higher than the power on the bottom. Okay, so really easy, even from looking at it, you can say, oh, well, that'll go towards infinity. Okay, so this is going to, so this will approach infinity. You can also say, oh, well, it's infinity over infinity, so you can use L'Hopital's rule there if you want. You can use L'Hopital's rule, what we did here. We do have other ways to do it besides using L'Hopital's rule, but you would get to the same conclusion. Okay, so does this converge or diverge? Divergent. Okay, so we're done. That makes sense. Okay, good. Let's just keep doing some more examples. Okay, so 26, we're asked to do the same thing, but the sequence in this case is an equals 2 plus 0.86 to the n power. Okay, now, before we do this one, we're probably want to give a little bit of discussion to talk about what if I have a number 2 of the n power, right? What's going to happen with that, right? So let's think through this, right? So if I have, let's see. Well, let's just take our number for now, right? So let's think about what's going to happen if I plug in each n term, right? If I take n equals 1, I just get 0.86, right? If I take n equals 2, I get 0.86 squared. Is 0.86 squared bigger or smaller than 0.86? It's smaller, right? 0.86 cubed would be smaller than that, and the next one would be smaller than that. The next one would be smaller than that, okay? So this is true, right? In general, if I take the limit as n approaches infinity, I'm going to just use the number r to the n. Then this is going to be equal to 0 if -1 is less than r is less than 1. Okay. Now, oftentimes we might just be dealing with positive numbers for the moment. Sometimes a negative could end up in there, but in any case, if if r is in between -1 and 1, and I put it in here, the limit of that thing is going to be 0, right? Because ultimately, no matter what the negative sign is doing, the number on the inside just keeps getting smaller, so it's going to approach 0. Okay, but happen? What's gonna happen if I wrote absolute value of r is greater than 1, but that just means r is greater than 1 or r is less than -1. What is it gonna approach in that case? I mean, in one case is, well, actually, let me write those separately. Let's just do when r is greater than 1 first. What is it? Good. It's just gonna approach infinity, right? Because whenever I take that number to the infinity, it's just gonna keep getting bigger, so it's gonna go towards infinity. Okay. What's gonna happen? What's gonna happen when r is less than 1, right? So if I have like -2 in there or something, right? I guess I could even include 1 there if I wanted to, or include -1 if I wanted to, but if I take -2, right? It's gonna, not only is it gonna keep getting bigger, but it's gonna consistently fluctuate between up here and down here, up here and down here, right? So this one just simply does not exist. Okay? So these are important to keep in mind, right? And then there's some obvious ones which I mean, I didn't write when r equals 1, but what's gonna happen when r equals 1? It's just 1, right? Because it's just 1 to the n power, which is 1. Okay? So in that case, it's just going to be 1. But so this is something important to keep track of, right? So if r is in between -1 and 1, it's going to be 0, and otherwise it might be problematic. Okay? Good. But for our example, it is in between -1 and 1, right? So what's the limit of this piece as n goes towards infinity? 0. What's the limit of this piece as n goes to infinity? 2. So we just get 2 plus 0. Okay. So what does that mean? Is it convergent or divergent? Convergent. Good. And it converges to 2. Okay. Any questions for me? Okay. I'm going to do one more example for now, at least. And then I'm going to talk about, this, give lip service to those definitions. There's a proof for this last guy in the book, but it requires, if you plan to take real analysis at any point, this will all come in handy. Because you actually learn this stuff before you learn how to do limits and derivatives and stuff technically, so it's actually pretty important. Anyway, let's do one more example. Let's see, do I want to do, well, no, let's do something different. Which is going to be cosine an equals cosine of n pi over n plus 1. Okay, so here's my function now. And I want to find the limit of this thing. Or I want to see if there is a limit at all, if it's infinite or if it converges to something, right? So I'm going to take the limit as n approaches infinity of cosine of n pi over n plus 1. Now, to do a problem like this one, right? What's going to be really nice is this last one I actually wrote over here, which is that if I have the limit as n approaches infinity of some function of an of like maybe some sort of sequence thing inside, then that's the same thing as f evaluated at the limit of that sequence. So I can just bring that sequence inside, but it's only if my function is continuous at the points I'm looking at. Okay? Is cosine a continuous function? Yes, it is. It's like a really a good example of continuous function. So this is the same thing as the cosine of the limit as n approaches infinity of n pi over n plus 1. Okay? What is the limit as n approaches infinity of n pi over n plus 1? What do you think? A few ways to do it. You could use L'Hopital's rule. You could do, just take the constants in front of the terms, whichever. What is it going to be? Anybody, help me out. On 0, it's pi, right? You can do what we call rule, so we take the derivative of the top and bottom, so you just get pi over 1, it's pi. Or we could use divide the top and bottom by n, so we would get pi over 1 plus 1 over n. But the limit of 1 over n is going to be 0, so we just get pi over 1. In other words, it's going to be pi, which is what? -1. Good. So is this convergent or divergent? Convergent. And then its limit is that. Okay. Good. So just some more limit practice really in this section. So that's going to be great. Someone asked you just naming things here. If we have, I don't know, just in case you want to practice more questions than the one I gave you, but I feel like it's important to mention. We call a sequence increasing if all of its terms, if the next term is always greater than the one before it, and we call it decreasing if the last term is always greater than the one before it, right? So they're either always getting bigger or always getting smaller. And if they're either increasing or decreasing, we give them a name monotonic, which just means that they're always doing the same thing. They're always going up, or they're always going down. Okay. And then they're bounded if, so for example, on this, like, in reality, this sequence is always going to be less than pi, because there's no numbers I can plug in that perfectly to pi unless I go all the way through infinity, right? So this just means that this is smaller than some real number m. If it's bounded below, then it's always bigger than some number. And like obviously, both that sequence inside is always going to be bigger than 0. It's always positive, right? So that's an example. And then we have a last theorem that just says that if this is true and this is true, then it's going to be convergent. So that'll be fun to experiment with and talk through, but I wanted to at least mention it. Yeah, but there's some examples. I have a few examples on the homework. Yes.
Would you put that on the calendar sheet?
That?
Yeah.
You won't need that. That's what I was just saying. Like, I want to mention it because the book puts a very important one, so I want to. I'm not going to ask you to use that because again, to even, I mean, really to be able to use it and analyze it, this requires this class is not. What?
We'll have other ways to solve it.
Well, yeah, this, right? You would just be doing this, and that's it, right? This is more technical terms. For I mean, what we're doing here technically, I mean, some of this is happening behind the scenes, but you just need to do the limits on those. So these, all the ones I did as examples in class are going to be the ones you have. Okay, good. I'll stick around for a bit if anybody has any questions. Where? Oh, here?
Yeah.
So that means, yeah, and the one definition I had, that was, that little n meant natural numbers, so that just meant 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Your regular, no negative numbers, just like your positive integers, essentially. And then R means real numbers. So that means just any number that doesn't have I in it, right? That's real, right? So there's a wide range of numbers you can pick for these, but yeah, that R means real numbers.
The N, is that like?
That's just some number, yeah. It doesn't. It's just like an abstract. You could use like big B there or something, or big T, big whatever. It doesn't matter.
It doesn't mean clarity of the non.
Yeah, it's just the letter used, the variable used. So that's fine. Yeah, do you have it with you, or are you going to turn it online?
I'll submit it online.
Okay, that's fine. It should. I think you should still be able to turn it in, so it's not that big of a deal. Yeah. Any other questions for me?